Can you write so much?
Bro, you guys got like 8 cars at your house. Why is
Okay, so let's do this up there because I think everybody just kind of got done with one set of trials. So, and if there's, like I said to you yesterday, if there's ever a lab that gets sketchy, it's this, mainly because if you look at everything that can go wrong, okay, and there's a lot of things that can go wrong in this lab. So even if you look at, and I think Party Girl, your group had that trouble where you had the pipette, okay, and you heated it up and you heated it up, and you still had a little bit of that left in the bottom, and you couldn't get it all to evaporate out, okay? So that could become an issue, because in theory, all of this would boil off, that would be completely filled with vapor. Boom, you'd put it into the water bath, all of it would condense, and that's the only liquid that you would get is just from that condensation. So that's a potential issue. You have, because realistically what is going to happen is that even if this thing was completely filled up, and that as that vapor condenses, it's basically going to create a vacuum, and you are going to draw some air into it, okay, because it's open towards the top. So you are going to draw some nitrogen and oxygen into that, just because as that vapor condenses, something's got to take its place. So you're not going to have a pure sample of that liquid in there, okay, because it's just, unless you could seal it off and then let it condense, that's the only way that you would not have any introduction of air, of nitrogen and oxygen. Now, obviously, the longer that sits, after you take it out, the more nitrogen and oxygen is going to be introduced into that system, and that's where you're going to get more and more of an air. Even when you filled it up with water to get the mass of that water, maybe you didn't get all of that water out when you did the mixed trial, okay? So that's a potential source. So there's any number of things that could go south on this lab. And I looked at some of you had data, and actually for this lab it wasn't horrible, okay? I know you all are sitting there going, wow, this really sucks, okay? In reality, the data that I saw wasn't all that bad. So, so let's do a little bit of sharing of data. And so I've got those up there. So here's the idea, is that you should know how to do your calculations, okay, off of your data. So let's put that up there to see if we can see some trends. So I've got the different ones up there. So you need to write down the volume of each individual pipette. So that's, I kind of didn't leave enough room, so you'll have to kind of cram that in there in that top. And then
The volume of each individual pipette?
yes. And then the mass, and then what you calculated as that molar mass. And then we'll see if we can see some trends in terms of, hey, which section went best, which didn't. So send somebody up there to fill in that data, and we'll make some comparisons. So Thermo, can you stop that camera again, please?
Yeah.
Ooh, I'm gonna use a pretty blue.
Thank you.
You talking?
Okay.
Did it start, Bert? Here, I got it.
Yeah, no, it's gone.
It started?
Yeah, it's gone.
Okay.
Okay, so here's our accepted values. There's 46.1. We got one of 49.5.
Not bad.
Right, not bad. This one should be accepted value of 58.1 for the acetone. And the isopropyl should be 60.1. Okay, so let's figure out, okay, so here's what, let's figure out the process. Like, first off, what do you notice about all of the values relative to what they should be?
They're bigger.
They're bigger, right? They're bigger than what they should be.
Just a bit.
So look at this, right? So look at your steps. So at the end of the day, how did you calculate what was that last thing that you did to calculate molar mass?
Found the density.
Okay, so if you look at how you calculated molar mass, that was dirt, right?
Yeah.
Divided by the pressure. So where do you think you had the least amount of error?
The pressure.
Yeah, the pressure. Okay. Hey, I came in here, I looked at the CO2 monitor, and I got the pressure. So you got to figure that was a home run deal, right? And that was already in atmospheres, so we didn't have to do anything with that. So then you got your temperature, right? Okay, hey, that was the temperature of the boiling water. Well, probably not a lot of air there, right?
Mm.
Okay. Well, you had the ideal gas law constant. That's kind of a home run deal, right? Okay. It's constant. So look at how you calculated that density. So again, you could write this as either, you could actually calculate the density by taking your mass and dividing it by the volume.
That's right.
Okay? Now, so here's the deal. You were getting molar masses that were too big, right? Everybody's data, the molar masses were too big. Which leads us to one of two things. Either the calculated volume of the pipette was too small, and the mass was right, or the mass was too big, and the volume was right, or you could have a combination of the two. You had too small a volume, you had too big a mass. So look at this. So look at that process. So you had that pipette that you had heated up, right? Okay? And you filled it up with water. So do you think, if you look at how you calculated the volume of the pipette, what did you do to get the volume of the pipette? How did you get that volume?
Find the water,
Find the mass of the water, and then what?
and then the density, using the density.
Yeah, so the density of water is mass divided by volume, right? So to get that volume, you're going to take that mass and divide it by that density. Okay? What'd you use for the density?
The 0.9973.
Yeah. So that 0.9, was it 997?
3.
Yeah.
9973.
9973. Okay? A little bit less than 1 gram per cubic centimeter. Probably could have just rounded it up, right? And then you had the mass. Well, you probably didn't screw up the mass of the water, okay? Because there you go. I mean, it's just like, hey, fill it up, let's find the mass. Boom, here you go. So the only big source of error that you could have would be the mass of this, the mass of the gas inside the tube. So this volume probably you didn't screw up. The pressure was a known value. The temperature, I'm guessing everybody's temperature was what, 97, 98?
I had 94 and a half.
Okay, right, something around that ballpark, right? So how could, especially your group, okay, the Bodie group, yes Bodie, we're talking about you, okay, the Bodie group, so why are your numbers so astronomically big? What happened?
We had the extra liquid at the bottom.
Yes.
Evaporate.
Okay, they didn't get a chance to run it long enough, and it's not a fault of them, we just ran out of time. But when they looked at that pipette, they hadn't evaporated all of that water or all of that liquid out of the bottom of it. So then when they found the mass of it, it made it look like that molar mass was much bigger than it should have. So I'm guessing that's typically the source of error, is that you're assuming that all of the mass in there was solely because of that condensed liquid. And if you weren't able to get all of that liquid fully boiled off and into a vapor stage, that's what's going to happen. So I guarantee you, your source of error, because like this one, 70, this was actually pretty good except for that 109. You got one that was pretty good. These, okay. Oh, well, let's not talk about that one. And these are a little bit more reasonable for that acetone. Yeah, you were wrong, but you were consistently off. Okay? Yeah. If you're going to be wrong, at least be wrong all the time. So that way everybody knows kind of what to expect. So anyway, so for those of you in the studio audience, you need to pick one of these sets of data. I don't care which one. Let's just do the ethyl alcohol.
Ooh.
No, Bodie will have that one. Riley, so somebody give me your temperature of that ethyl alcohol.
94.5.
94.5. So that was the temperature, and then
That was the boiling temperature.
And then what was the atmospheric pressure that we used?
0.967.
9.67 ATMs. Okay. So that's what you're going to need to do one of these sets of calculations. Okay. We're good? Got it? Okay. So that's what, in reality of science, if you look at things that are train wrecks and you go, okay, hey, what happened to cause the train wreck? Okay.
Can we look at 2A and 2B?
We can talk about that.
All of your computers would come crash.
Oh.
Oh, your phone's about to fall off your desk.
Huh?
Your phone's about to fall off your desk. That one?
Gravity.
Gravity.
I know.
The air
Okay.
molecules are pushing her.
So anyway, so which questions do you want to ask? What do you want to talk about?
2A and 2B?
Like the pre-lab questions? Okay. So here's the deal. So if you look on 2A, only part of the pipette was immersed in boiling water, so the temperature in part of the pipette was less. So this might have been what happened. So if you look at what happens, like in that pipette. So let's say here's your water level, right? And so obviously this lab will only work if you do liquids that have boiling points below the temperature of water. Okay, so this is why I picked these. So if you look, your boiling points are all, the highest boiling point was isopropyl alcohol, which is around 82 degrees. Okay, that's the highest boiling point. So what happens is that as this thing boils off, right, and you turn it into a vapor, what happens then is if you're assuming that we're basically going to clear all of this out and it's all going to be as a vapor when you pull this out. Well, if you don't have that whole thing at that temperature, what's going to happen is it's going to reach this cooler air up here and then it's going to condense back down.
To a liquid?
Yes.
Okay.
Okay, because it's not, everything isn't above that boiling point. So instead of having, because you're assuming that when you put it in the water, everything that condenses was just filling up the volume of that pipette. So if you don't have it warm enough, then you already have some condensed liquid in there. And I guarantee you that's what happened with Bodie's group, because you all had a bunch of liquid that was already in the bottom, and that's why you all have such high molar masses. Okay? So then on B, it's kind of the same thing. That was a question about will stand for a while. So this is what I was talking about. If you let it stand for a while, you're going to create a vacuum. And as that vapor condenses, the pressure on the outside is remaining constant. So as that condenses, air is going to come in and take its place. So then, I'll just say this for Fulton's sake, that air molecules are going to rush in. Okay, Merry Christmas.
On video now.
So air molecules will rush in, and you won't have a pure sample of just that gas. And the longer it sits, If you let it sit long enough, you would basically be finding nothing but the molar mass of nitrogen or oxygen. But this is actually how they separate out, like how you separate from air is called like a diffractionating column. So basically what happens is that you take air and you reverse the process and you cool it down. And so as you cool that gas down, it's the reverse of what happens here. So as you cool it down, the one that will condense easiest, that's the one that separates out first. So as it cools down, oh, oxygen, because it's slightly bigger than nitrogen is as a gas, it has like a higher boiling point. So it's going to condense first, then the nitrogen will condense second. So this is why it's so difficult to have pure helium or pure hydrogen, because you have to get everything so cold to allow those London dispersion forces to kick in and make it sticky enough to exist as a liquid. So if you look at all these liquids, okay, that you all dealt with, they obviously have pretty strong intermolecular forces, and that's why they're liquids at room temperatures. Okay.
So how would the air coming in, how does that affect the molar mass?
It just, the assumption that you, when you do your calculations, is that it's a pure sample. So how it's going to affect it is that now you're going to have nitrogen and oxygen in there, so you won't get a pure value for that molar mass. That's all you have to say. So your structures, okay? You can look that up on the internet, your phone, whatever. So let's talk about the acetone, okay? So, oh, I screwed that up. Those are hydrogens,
I
not.
was gonna say, there's a couple carbon there. I mean,
What's a couple of carbons between friends?
exactly. I don't know.
I just tried to erase one with my finger.
Works. Can you write with your finger on there?
Well, you can move it,
You just
but you
can't
can't
write
write
with
with
it.
it. Okay, so let's talk about acetone versus, there's acetone. Now, is acetone going to have hydrogen bonding?
No,
Why not? It has oxygen, it has hydrogen.
The hydrogens are not attached to the oxygen.
Bingo, okay? So this is the classic example of where you have an oxygen and a hydrogen, but you do not have hydrogen bonding. Now, is this going to have a dipole moment?
Yes.
Yes,
Yes, this will have a dipole moment
because of the oxygen.
because that oxygen is going to have those lone pairs of electrons. So this will have a dipole moment in the middle that's going to point towards that oxygen. So if you look at it, in terms of that acetone, in terms of the boiling point, so acetone has the lowest boiling point. So let's talk about those values. Did I write them down up here? So here's the deal. So acetone is going to have the lowest boiling point. So what does that mean in terms of just generally intermolecular forces?
They're less strong.
They're less. Now, if you look at ethyl alcohol, right? Ethyl alcohol, ethyl means 2. And no, you don't have to know that for the test, but it's just kind of general knowledge. OH. And then you have iso, which means 3. And, okay, hydrogen. So here's the deal. So what makes them alcohols is what we call a functional OH group. If you study organic chemistry, you're going to learn a bunch of functional groups. So here's the deal. So if you look at a comparison of ethyl alcohol and isopropyl alcohol, notice that isopropyl alcohol, even though they're both alcohols, and they both have hydrogen bonding, why is the isopropyl alcohol boiling point higher than the ethyl alcohol is?
Because it has an OH group.
No, they both have OH groups.
Well,
It has a stronger LDF.
Why?
It's like more linear, so it's more polarizable.
Okay, well, there's that. But also, if you look at how many carbons are in isopropyl,
3,
3. How many are in ethyl?
2,
2. Which one is the larger molecule?
isopropyl.
Isopropyl. And the larger a molecule is, the easier it is to induce a temporary dipole moment. Therefore, it has stronger London dispersion forces. So, acetone also has 3 carbons. Okay, so if you look at the similarities, if you look at acetone and isopropyl, and this is what you got to be able to do for the test. If you look at acetone and isopropyl, okay, they both have 3 carbons. They both have a lot of hydrogens. They both have an oxygen. Okay, so this is what the struggle is. How do you explain the difference in the boiling points? And the difference is that acetone does not have hydrogen bonding, but isopropyl alcohol does. And that explains the difference in those boiling points. Okay? So you have very similar structures. They have the same number of carbon atoms. Basically everything is the same, except for where that hydrogen is bound. Okay? And that's what you want to be able to think through. Now, let's talk, there's another thing that we could do, and that we would have even got more screwed up results if we did this. Because it's even tougher to do, because you have to have a vacuum, okay?
Oh,
So if you look at vapor pressure, so let's talk about how vapor pressure is measured. So what you would do is that you would have like a test tube or something where you could measure the pressure, and you would evacuate it out, the vacuum, boom, and then you would put a little bit of sample of the ethyl alcohol, the acetone, whatever it is in there. And so what's going to happen is that this stuff is going to begin to vaporize until it reaches an equilibrium point, where the vapor is going, the rate of vapor going out is the same as the rate of condensation coming back in. Okay, so those two values, you're going to reach that point. So here's my question, and this is what you've got to be able to think through. If you look at ethyl alcohol, acetone, isopropyl, which one of those 3 is going to have the highest vapor pressure? Ethyl alcohol, acetone, or isopropyl?
acetone.
Acetone. Why?
Because it's the smallest
Okay, so here's the deal. It's the smallest what?
molecule.
No. Well, it is, but
Smallest boiling point.
it really isn't even the smallest molecule. That's the lowest boiling point, right? So there's an inverse relationship between boiling point and vapor pressure. So if you have a low boiling point, that occurs because it doesn't take much energy to break those bonds apart. Okay? So what that means is that if you take that liquid and just let it evaporate out, that acetone is much more easily changed into a vapor from a liquid. So these are going to be inverse relationships of each other. So the acetone has the lowest boiling point, but it's going to have the highest vapor pressure. The isopropyl has the highest boiling point, but it's going to have the lowest vapor pressure. Okay? So those two things are inverses of each other. Okay? So this is one of the, promise you. This is what you've got to be able to think through on that quiz, test, assessment, whatever you want to call it, on Monday. Okay? Anything else you want me to go over on the lab? Kind of went through about every question on the back side of it. So that's something that you got to know. Okay. All right. So there's that.
Eric, do you want to do me a favor? And just toss that in there? Thank you.
So the quiz / assessment on Monday, there's going to be 2 main parts. There's going to be like questions about hybridization. And bonding. And then there's going to be stuff about gas laws. Okay, those are going to be the two broad topics. So, in terms of hybridization, the only ones I'm going to ask you about are SP, SP2, and SP3. Okay, now there's actually like a lot more, like there's like SBDF5 and SBDF3, and it's weird stuff. Okay, I'm not going to ask you about those. I'm going to stop at SP3. Now, here's the deal. If a central atom, whatever that is, if it's bound to two other elements, that will always be SP hybridization because there's only two bonds that are formed, and that will only be SP hybridization. True or false?
False. Hold on.
True.
There's two areas of high electron density that it's SP.
Okay, hold on. So let's look at water. Oxygen, two hydrogens. So if that's the case, does water undergo SP hybridization? Does the oxygen undergo SP hybridization because there's only two regions of high electron density?
If that was the case, then yeah.
But the electron cloud makes it.
Oh, the electron cloud. So here I happen to have
Oh, of course you do.
Water.
That's supposed to
water. I've lost my water. Yeah, what happened? Oh, there's my
I got
water. I got it. We're back. Okay, so this just shows the atoms that make up water. Got an oxygen, two hydrogens, right? But how many valence electrons does oxygen have?
6.
6. 2 of them are tied up here. Where are the other 4?
Up above.
Up above. So remember, hybridized orbitals can do one of two things. You can use them to make bonds, but what else can you do? What else can they hold?
electron pairs.
An unbound electron pairs, or non-binding electron pairs. So here you have oxygen, yes, it has 2 regions of high electron density in the bonds, right? But, go away. Oh, seriously. Okay. So up here, you've got a pair of electrons here, you've got a pair of electrons there. Now, what's that going to do to that bond angle by having this dome of negativity up here? It's going to make this bond angle bigger or smaller?
Small.
Smaller, because it's going to force these down. What type of bonding do water molecules undergo?
LDF.
London dispersion forces, always London dispersion forces. Okay, what else?
Hydrogen bonding.
Hydrogen bonding, in case you have an oxygen bound to a hydrogen.
Can it
And
be dipole?
dipole. Which direction does the dipole moment point? Towards the oxygen or towards the hydrogen?
Towards the oxygen.
Towards the oxygen, because it always points towards the negative end. Okay? So, when you get into electron, so there's also terminology that you need to know. Electronegativity, electron affinity, first ionization energy. Okay? You need to know those 3 terms and how they play out. So, why do noble gases not have any electronegativity or electron affinity?
Because they already have their A.
Yeah, they've got the full outer shell. They don't care about giving up electrons, right? They don't care. It's not part of the story. They have all 8 game pieces on the Monopoly board. Okay, they don't have to worry about anything. What do you know about halogens versus alkali metals in terms of electronegativity?
That alkali metals have a lower electronegativity.
Okay? And because halogens have 7 game pieces, they really want to gain 1 more. So halogens have very high electronegativity. They also have very high electron affinity because they're willing to take those electrons in to form those bonds. So you have oxygen. It has 6 valence electrons. It's going to bond with that hydrogen. I'm not going to expect you to do formal charge. Okay?
Oh, thank
Okay?
God.
Do not worry about doing formal charge. I am not going to make you do formal charge on the test. Okay? So don't worry about that. So let's talk ammonia. NH3.
Let's do it.
Okay? So ammonia has 3 regions of high electron density. So does it undergo sp2 hybridization?
Yes.
No! How many valence electrons does nitrogen have?
5.
5.
5. 3 of them are here. Where's the other 2?
Oh, up there.
Up here, right?
Sorry.
It's up here.
Sorry.
So guess what? Water, ammonia and water both undergo sp3 hybridization. Okay? Because you've got a pair of electrons up here. Now, let's talk ammonia, right? Ammonia is very soluble in water. Why?
Hydrogen bond.
That's kind of it.
It's polar, but no negativity attracts the hydrogen.
Okay? So you have, if you look at this in terms of a dipole moment, ammonia is going to have a dipole moment, water is going to have a dipole moment. This is going to have hydrogen bonding, this is going to have hydrogen bonding. So it's one of those deals, likes dissolve likes. So ammonia is extremely soluble in water because of the fact that they have very similar properties on an atomic level in terms of their structure. Now, carbon dioxide. You always see carbon dioxide, chunks of carbon dioxide, otherwise known as dry ice, right, dropped into water. What does it do? Does it dissolve in the water or does it bubble up?
Bubbles.
Bubbles up. You know why? Because carbon dioxide is vastly different than water is. Okay? It's CO2. Okay? It's a linear molecule, right? So if you look at CO2, CO2 isn't anything like water. It doesn't have hydrogen bonding. It doesn't have a dipole moment. So carbon dioxide is not going to dissolve in water because of the fact that the structures are so completely different. But ammonia will. All right. Now, the classic one is methane, CH4. Does that undergo sp3 hybridization?
Yes.
All day long, okay? All day long. And that's the classic sp3 hybridization, okay? Because you have the 4 regions. So, here's the other thing to think of. Let's say that you have a carbon and it's going to form a double bond with another carbon. And let's say you have a hydrogen here, a hydrogen here. Hydrogen here, hydrogen here. Mr. Doyle, how many regions of high electron density do I have around that carbon? 3, okay? So it has 3 regions of high electron density. Perfect. This is going to make a double bond, right? Mm-hmm. So when you have a double bond, what 2 types of bonds do you have?
Sigma.
Sigma and pi bond. Now, Mr. Doyle correctly just told me that there's 3 regions of high electron density around that carbon. Okay? So if I have 3 regions of high electron density, what type of hybridization does that undergo?
SP2.
sp2. So this is going to undergo sp2 hybridization. Now, if you undergo sp2 hybridization, you screw up the s and 2 of the p's. But that leaves the 3rd non-hybridized p orbital, which is going to allow you to do what?
Pi bond.
Pi bond. Because remember, you have to have a non-hybridized p orbital to make a pi bond. Okay? So what's going to happen here is that you've got a sigma bond here. Here are your other sp2 hybridized orbitals around here. So then around this, you're going to have, each one is going to have a non-hybridized p orbital. Boom. That's how we can form that pi bond. So the sigma bond is going to exist here, technically known along the interatomic axis. And then you're going to have your pi bonds out here. So if you had a triple bond, let's just say, you had a triple bond between 2 carbons. How many sigma bonds are you going to have? 1. How many pi bonds are you going to have? 2. So you got to have 2 sets of non-hybridized p orbitals. So if this is your structure, what type of hybridization is the carbon undergoing?
SP1.
sp, right? Just sp. So I've got 2 regions of high electron density. So that means I have 2 p orbitals that are left non-hybridized, and that's what's going to make it. So here's the deal. So if you look at a triple bond and a double bond, right, and then a single bond. So if you were to look at these, in which situation do you think the carbon atoms are going to be closer together? The single bond, the double bond, or the triple bond?
The triple bond.
The triple bond, because you have 3 bonds that are pulling those carbon atoms together to overcome that natural repulsive force. Because the nuclei don't want to be near each other because they're positively charged. Now, here's the deal. Which one do you think is going to have the greatest bond enthalpy? The triple bonds, the double bonds, or the single bonds? Triple bonds. Because if you were going to separate this out, you'd have to break 3 bonds. So this is going to have a lot higher bond enthalpy than the ethane is. Okay. So if you were to just look at these structures, okay, if I just gave you these 3 and said, okay, so you've got single bonds, double bonds. So in terms of, if you were to look at this in terms of ethyne, what would the advantage if you had 2 of these? Why would you tend to think these would have stronger London dispersion forces if I had another one? Why would this have stronger London dispersion forces than the other 2? It's linear, right? So these 2 could like snuggle up beside each other, and they would have a lot of surface area contact. But this doesn't have as many hydrogen atoms. Okay, so you're going to have probably going to have stronger London dispersion forces, but because it's linear, but you don't have as many hydrogen atoms to induce a overall induce a dipole moment. So that's going to kind of be your trade-off on that. Okay, ideal gas law, be able to do stoic with gas laws. Okay, there's a problem on this review. Make sure it's the last problem on here. It's a reaction between hydrogen and nitrogen. I beg of you, if there is nothing else, make sure that you can do this one, okay? Because I promise you there's going to be some stoic involving gas laws on there. So make sure that you can do that, mainly because that gets complicated because then you're generating gas, and that's going to add to the volume, and you have to worry about that. Okay, so I am done. So you've got the last half hour. If you can get that lab done, that would be great. Then you've got, like I said, you have the blank review, and then you have the one with the answer key to it. So here we go, boys and girls. Yeah, stop that.